OK, so last time we talked about the zeroth law, which is the common sense law, which says that if you take a hot object next to a cold object, heat will flow from the hot to the cold in a way that is well defined. And it allows you to define temperature. It allows you to define the concept of a thermometer. You have three objects. One of them could be a thermometer. You have two of them separated in distance. You take the third one, and you go from one to the other, and you see whether heat flows when you touch one object, the middle object between those two objects. And then we talked about temperature scales. We talked about the Celsius scale, the Fahrenheit scale, and the late 1800s were a booming time for temperature scales. People didn't really realize how important it was to properly define the reference points. Fahrenheit's warm-blooded, or 96 degrees. Roemer, 7.5 degrees Roemer, because he didn't want to go below 0 degrees and measuring temperature outside in Denmark. Those are kind of silly. But they're the legacy that we have today. And that's what we use. In science, we use somewhat better temperature scales. And the temperature scale that turns out to be well-defined and ends up giving us the concept of an absolute zero is the ideal gas thermometer. So let's talk about that briefly today first. The ideal gas thermometer. It's based on Boyle's law. Boyle's law was an empirical law that Mr. Boyle discovered by doing lots of experiments. And Boyle's law says that the limit of the quantity pressure times the molar volume, so this quantity here, pressure times the molar volume, as you let pressure go to 0, so you do this measurement, you take a gas, you measure the pressure and the molar volume, then you change the pressure again, and you measure the pressure and the volume, you multiply these two together, and you keep doing this experiment, getting the pressure smaller and smaller, you find that this limit turns out to be a constant, independent of the gas. Doesn't care what the gas is, you always get to the same constant. And that constant turns out to be a function of the temperature. And the only function it is, it doesn't care what the gas is, it only cares what the temperature is. All right, so now we have the makings of a good thermometer and a good temperature scale. We have a substance. The substance could be any gas. That's pretty straightforward. Okay? So now we have a substance, which is a gas. We have a property. It's not the volume of mercury or the color of something which changes with temperature or the resistivity. In this case here, our property is the value of the pressure times the volume, times the molar volume. That's the property. The property is the limit as p goes to 0 of pressure times molar volume. It's a number. You're going to measure it. It's a number. It's going to come out. That's the property that's going to give us the change in temperature. Then we need some reference points. And Celsius first used the boiling point of water. The boiling point, and call that 100 degrees Celsius. And the freezing point, and call that of water, call that 0 degrees Celsius. And then we need an interpolation scale. How to go from one reference point to the other with this property. Okay? This property, which we're going to call f of t.